So now let us move to a very important concept we call conditional probability. So the main idea is that if you have event A, and we can study the probability A happen, right, by looking at PA. But the question now is that, say, if I have some additional information about some event B that already happened, will the likelihood happen of A change or not if there's additional information available to me, right? Here, the conditional probability, the probability of A occurs given that B occur, we know by P, A given B, okay? And A and B, we call it two independent events if we have the probability of A given B equal to probability A. So which means that B occur not, it had nothing to do with A, okay? And if it's not the case, right, we see A and B, the dependent event. Dependent event. So let's look at the example. We have three events. Dark. It's dark outdoors. We denote D. M is the event that is midnight. And F is the event that the stock market will tomorrow. Okay. So roughly speaking, okay, we can see that the probability dark outdoor is 12 by 24, right? It's half, right? So say, you have half of the is the daytime and half is the nighttime. Okay. So roughly speaking, okay, we can see that. It may vary by different regions, but more or less, and just roughly speaking, that's the probability we get for dark outdoor. The probability of stock market go up tomorrow, just put half, right? We don't know, maybe up, maybe down. So let's see. So say if we given M, which is it's midnight now, right? So in general, we can see that the probability of F, the stock go up tomorrow, it had nothing to do, right? Given that it's midnight. So it's still equal to F. So it doesn't matter, it's midnight or not, right? It won't affect the probability of stock market go up tomorrow. But say if I consider I know that it's midnight, right? So for sure, yeah, it's correct for most of the region, right? It must be dark outdoor. So you can see like the probability of PD given M now equal to 1. It's different with D, right? Different with D. So from that, you can see that F and M, the independent events, midnight and stock market go tomorrow, the independent, right? But say D and M, D is the dark outdoor and M is midnight, they dependent, right? Dependent. Because if we know one, right, it affects the other one, right? Property happen, right? So this is the formula how we calculate the conditional probability. So say the probability of A given B, now it become probability A and B divided by B, okay, B. So basically, like the logic here is that like if I know B already happened, right? To calculate the probability of A, I will narrow down my search area. Instead of searching in the whole area of the whole sample space, I will narrow down to only the B, okay? So my sample space now just B, okay? It will be shrink down, right? Shrink down. And because my sample space is just B, right? So even A I consider now it has to be the intersection with B, right? So it gives me the formula. And with this formula, we can also, just flip BB to the other side, right? So we can get like PA and B equal to BA given B times BB. So it gives us the first equation in the multiplication rule. But because you can also know that the union operator, okay, A and B are being A, they are the same. So we can flip, right, it. And from that, you can also get PB equal to B given A times BA. So this is called multiplication rule. And in a special case, when you have an A and B independent, at that time, you can see that BA given B equal to BA, right? BA given probably B given A also equal to BB. So basically, like if we have the independent, and then our life will be much similar. At that time, we only have like the condition no here, it will be removed. And basically, at that time, probably A and B equal to BA times BB. Okay. So now let us look at an example 3 to 4 so we can get a better understanding about conditional probability. So say find the probability you roll a die and get a 6, even that you got an even roll. Even roll. So say if you roll a die and probably you get a 6, will be only 1 6, right? Will be 1 6 for a fair die. But now I give you some additional information that your roll actually get even, right? So if that's the case, then our probability will change, right? Change. Well, probably you get a 6 given, you got even number, right? So that time, we just use formula, right? A given B equal to B, A and B divided by B, B, okay? So based on this formula, we can see probably you get 6 and even, divided by probably even. And probably you get even phase will be 3, 6. 6 and even basically it's just 6, right? So it's 1, 6. So this probably will be 1/3, okay? Here, find probably such or draw a card and get a heart given she drew a red card, right? He drew red card. So probably heart given red, right? The same thing. Heart and red divided by red, okay? So again, you see that the sample space now is constrained, right? Instead, you look at all 52 cards. Now you only look at the red card because you only know that, right? He got a red card, right? So in this case, probably a red card will be 26 by 52, which is the denominator, and the numerator, hard and red. The intersection will be hard, right? Hard and red will be hard. So you have like 13 card hard, and which is 13 by 52. And it gives you half. Yeah. Now we look at another example from criminal justice error. So in 2005, 19.1% of all murder victims were between the age of 20 to 24 years old. Also in this year, 86.9% of murder victims were male, given that they from 20 to 24 years old. Okay, so this is the information we get. And so pretty much like kind of high for this age, right? About almost 20%, 19.1%, and pretty much most of them are male, right? 86.9%. So here, like, we need to find a probability that a randomly selected murder victim in this year was a 20 to 24-year-old male. Okay. So how we can answer this question, right? So here, like, let's we know let us denote A, the event that the victims are aged between 20 to 24-year-old, and B, the event that with a male. Okay. So we break down our problem a little bit by look at a similar event, right? Before we look at the complex event, which is was built based on this simple event. Um, so here, like, we have that if A, the event that the victim the age between 20 to 24-year-old for this year, right? 2005. And we can get that PAE 0.191, right? Because here we say that we see that 90.1% of the victim between 20 to 24, right? And also, like we see that if we know that the victim was 20 to 24, we about 86.9% sure, right? That a male, right? Based on the data we get, right? So probably B given A is 0.869. So given all those, we can see that if the event we care about, we want to find probability is that the selected murder victim in this year was a 20 to 24-year-old male. So this is the N event, right? Male and 20 to 24-year-old. Satisfy both properties here, right? So here, like this is A and B. So from the multiplication rule, we can see that BA and B equal to BA given B times BB, or BB given A times PA. So either way, right? So from that, given all the information we got here, you can see that BA and B equal to BB given A times BA, right? Yeah. We use the multiplication rule. So which is A69 times 191, right? And we got 166 here. So we can get this probability. So now let us look at example 326. Rachel draw 2 cards from a 52 card deck. Find probability that both cards are heart, even. So the first case is her first card is a heart, and after the first draw, she put the card back in the deck. Okay, then shuffle into a second draw. In the second case, also same setting, right? But slightly different. Her first card is a heart, but after the first draw, she didn't put the card back. Okay, so she keep it and shuffle the remaining 51 card into a second draw. So there are two scenarios, right? One scenario, the first one, she draw one card and she see the heart, and then she put it back and shuffle, and she draw another one from the 52 card, right? Because she already put it back, right? So second scenario, when she draw it, she see a heart and she keep it, and she shuffle the remaining 51, and she took a second draw. So the answer for this example will be different, depends on the setting, right? Setting. So if you know the A, the event, the first card in heart, B event, second card in heart, right? And A and B will be both heart, right? And this is the event we care about. We want to find probability that both heart, right? So we know that if for the case you put the card back, right? We call so basically like everything just like beginning, right? So at the time your sample space used to have 52 cards. And the event, the probability you get the second card in heart is just 13 by 52, right? Because you put it back, so you get the whole deck, right? And 52 card, and the probability you get heart would be 13 by 52. So from that, you can calculate probability of A and B be equal to probability B given A times A, right? A. And which is 13 by 52 times 13 by 52. Because the first draw, the probability you get a heart is also 1352, right? 1352. So you got like 0.063. But in the second case, our line will be slightly different, okay? Because we do not put the first card back, right? We do not. So in that way, you can see that the probability of B given A change, right? Change. Because you did not put the first card back, right? So which means in your deck, now you only have 51 cards. And you only have 12 heart, right? Because the first one is heart. So probability B given A will be only 12 by 51. And so this is the main difference if you don't put the first card back. And given that the first card is heart, right? Heart. So probability of the second card is still heart. Given the first card is heart is heart is only 12 by 51. It's no longer 13 by 52 like in part A, right? So from that, again, you can use the multiplication rule. BA and B equal B given A times BA, and be like 12 by 51 times 13 by 52, which is 0.095. So from here, you can see that the event A and B for part A, when you put the card back, right, they're independent. Because you put a card back, so the first time you go get a heart, and the second time you get a heart, it has nothing to do, right? It has nothing to do with each other. And then here we are, this sampling strategy, right? So you draw a card, basically just like you sample, right? You're sampling. In this sampling strategy, we call sample with replacements. And events that result from this can be treated as independent, right? So here A is the event, the first is the heart, B event, the second is the heart, they're independent. Maybe if you consider C is the event, like the second draw is a space, something like that. It's also independent, right? Because you put the card back, so it not affect the sample size at all. But for B, you can see that if you don't put the card back, our line will be different, right? In this at the time, A and B will be dependent. Okay. Because you didn't put a card back, so the consequence is that our sample space will get smaller, right? Smaller. So in the case we have a small sample space, so it will affect a lot, right? Affect a lot. So in sampling this way, we call sample with L replacement. So this is why the first draw is hard, right? The second draw is hard. If you didn't put a card back, the first draw will affect the property of the second draw, right? Because after the smallest guy effect is that it shrink down the sample space. And when we work with probability, we love to have the independent, right? Because independent make our life much simpler, right? So you can see here the formula, right? If you have independent, you don't need to do the conditional at all, right? Just a P A and B equal to P A and times P B, right? If A and B independent, then P A and B equal to B A times B B, right? So the good news is that actually, if your sample size is roughly speaking, less than 5% of the population size. So if you draw a sample which is less than 5% of the population, then we can treat the event results from either approach as independent for simplicity. Okay, simplicity. So pretty much like it tells us like we can get a pretty nice close result. Okay, if your sample size less than 5% of the population. So even you can sample with error replacement, but you can also treat it as an independent case. And for sure, if you have the percentage much smaller, the approximation will be very good, very good. So say, if your sample size you take out maybe just 1,000, one out of 1,000 compared to the whole population, and then for sure we can treat it at independent. So now let us look at another event we call Alice 1. So the probability of Alice 1 event often it's kind of complex if we want to work it directly, but will be easier to handle if we use complement rule. Okay, so this is a trick we use when we work with Alice 1 event, is that the probability of Alice 1 equal to 1 subtract to the probability of none of them. So say here, like we look at example, like we draw 2 cards, right? From a deck of 52 cards with replacement, which means we put the card back after each draw, okay? So if we didn't know A the event, at least one card is red, okay, one card red. So if we want to do the direct calculation here, we need to do the first card is red, right? And our second card is red, right? Because at least one red, right? And then we can use a more addition rule, right? First red plus second red, subtract first red and second red. And from that, you can see that first red will be 26 by 52. Second red is 26 by 52 because we put it back, right? And subtract by half, which is 26 by 52 times 26 by 52, right? They are independent, right? Independent because we put a card back. So the first row has nothing to do with the second row result. And then if we do this calculation, we got 0.75, right? 0.75. It worked with the direct calculation, but it's a bit complicated here. But now let us look at how we use complement rule here. So at least one red is a complement if none of them is red, right? So we can use one subtract to none of them red. And none of them is red for 2 cards, which means both black, right? Both black. Club, spade. And which means the first black and the second black, right? And they independent. So you can use it 1 subtract 26 by 52 times 26 by 52, right? So other time you just get 0.75, very easy, okay? So for this example, we use direct calculation and complement rule both work, okay? But for sure, you can see at the first degree, right? The complement much more effective. But outline will be difficult, say, okay? If we think a little bit further, what if I do draw 3 cards or 4 cards, right? And put them back. So say if I draw 4 cards, right? A 3 card, right? With replacement. A 4 cards with replacement. Or even 100 cards with replacement. And I want to find property, at least one of them is red. Okay. So let's say draw 3 cards with replacement. Find the probability at least one is red, which is the first red or second red or third red, right? So other time you see that it can work with direct calculation, but outline will be very complicated, right? Complicated. And say, if you have the 100 card draw, right? Draw 100 card. What probably at least one is red. So imagine, right? It's pretty much impossible if you do direct calculation. But if you do the complement, right? And say just none of them is red, right? And you just time 26 by 52, 26 by 52. So if you have even 1,000 raw, right? Just 26 by 52, you do 1,000 time, right? And one subtract to that. And you get the result. If you do 3 raw, you'll be 1 subtract to 26 by 52 times 26 by 52 times 26 by 52. So pretty much the 26 by 52 power to the n here, n is a number of draw, right? 1 subtract to that will give you at least one red. So this at least one here is also actually applied a lot in the real life, right? Real life. So here in aircraft safety. So an aircraft engine, often, they have extra engine, okay, for safety. So in case one fail, the other will get activated and still can take care of the flight. So aircraft engine, say it has a failure probability 0.01, which is 1 out of 1,000. Okay. So here, like engineer, they design 2 extra engine, okay, to increase safety. Okay. So what a probability of aircraft not fail, right? We do care about that, right? We don't want to fly in aircraft or airplane, right? And get the engine fail, right? So you can see that if you design 2 extra engine, right? So which means the aircraft they have 3 in total, right? And one do the load, right? The other 2 for in case something wrong happen with the main engine, right? So the probability of the aircraft not fail will be, which means at least one work, right? Because one works, the airplane still fly, right? And from that, you can see that it's just one subtracted probably all failed. And all three fail, you can see that just 0.001, the first one failed, right? Time the second one failed, time the third one failed, right? So here we assume they are all independent, right? Because they're just a different engine, right? And from that, you can see that this very, very, pretty much very safe, right? Very, very safe, right? When we fly on the aircraft. And not to mention, they get also maintenance very regularly. So you can see like, it even if you design here two extra, right? So you see like the safety increase significantly from a 999.999, right? To that's much digits, right? More digits. So kind of power, right? Power. The failure reduced to power of 3, right? So beside the aircraft example, in real life, right? We also have different kind of strategy engineers they use to uh, design um, the material to increase the safety, right? Avoid failure probability. So this is we call redundancy idea, which is basically they duplicate or triplicate, right? So in the aircraft example, they triplicate, right? Critical components to increase safety. So in aircraft example, often they have two extra, right? Two extra to increase safety. Here, like in another example, like the bus, right? Bus, they have the light at the back, right? So instead of just having two, four lights, right? They have extra, yeah. So in case some of the lights fail or broken, right? Others still work, right? So which means it increases safety when it suddenly stop. Bridge, right? Bridge here, you can see that uh, they will design multiple holder here, right? To avoid the bridge fail, right? Collapse, right? So the multiplication rule here, it gives us the probability of system fail, right? A product of each component fail. So we see in the example aircraft safety already, but basically like this is how it applied, this rule applied in real life, okay, real life. Here, a bonus, the multi-hole problem. And so this is a famous problem from a game show, Monty Hall, about 30 years ago, almost 25 years. So basically, in this game, you have like three doors, and then behind one of the door will be a car, okay, and behind the others will be goats. And say here, if you pick a door, say door number 1, okay, and for sure you don't know, you just can get give a guess it had a car, right? You want a car, you don't want a goat. And say after you pick your door, and the host, he or she will open another door with uh, a goat, okay, a goat. Because the host, he know which door has a goat or which door has a car, right? And he asks you, okay, now you know that, right? The door I just opened has a goat. Do you want to change your mind by switching the door or not, right? So the question here that if you're a player, right, and you want a car, you want a goat, whether you should change or not, okay? You get more information, right? So think about that, okay? Yeah. This is a famous problem, and actually you can find a solution easily on the internet. And we have Wikipedia, they do an excellent job in the reframing this problem. Okay, so if you're curious, just think about that, right? Should you change or not, right? And why not? I will leave it as your homework for curiosity. So now we look at the last part of the chapter, a contingency table. So contingency table is a table where we have two categories of data related. Okay. So here's some examples here. We have the gender, which is one category of data, right? Boy or girl. And like sneaker or not, right? Which is another category. A person like sneaker or not, right? So a person they can maybe can be boy or girl, right? I can like sneaker or not, right? So here we have a contingency table. The first one, boy or girl, like sneaker or not, right? We if we look at the house in a region, right? So we can look at one category, which is the number of bedroom of a house, right? 2 beds, 3 beds, or 4 beds. We can also look at a category with the location where it is, right? Chattanooga, Knoxville, and Knoxville, right? Knoxville. So if we related these two, one in the row side and one in column side, we get a contingency table. In the same thing, right? Gender and what kind of treat they want. Cake, ice cream, right? Or donut. Or maybe say we look at people say, the reburchase behavior category, right? Yes, maybe a no, right? And related to with the satisfaction level in terms of the taste, right? Satisfied, okay, and not satisfied, right? So if you relate those two categories of your data, okay, and you put it in a table, and we can construct something we call contingency table. And actually, from this kind of table, you can learn a lot of useful information, okay, how the thing related, okay. So here an example about Titanic disaster. Here survival data, the real data, and we got like 334 men survive and die 1360. We got 318 women survive and 104 die. And we also classify a little bit further for boys and girls. Okay, so maybe men, women who bigger than older than 18, right? And boy and girl less than 18. So boys is less than 29 survive, 35 die, and girls 27 survive and 18 died. Okay. So here like some probability we can look at, right? When from the contingency table. So here like find the probability a randomly selected individual is a man who survived. Okay. D. And B, probability that a random selected individual who is a woman or die. Okay. And C, the random selected individual is a boy given he died. And D, a random selected two individual where at least one of them is a man. Okay, so this is the probability we're going to find from this contingency table. So often before we go any further, okay, we will need to reconstruct some of the sum to make our life easier. So you can see that, for men survive and die, from our original table, we can find out that the total number of men survive, right? Total men. For the women, you can find total women in 422 here. For the boys, you can also add up. Survive and die, you get the boys and girls. And you can also find the category of survive, including men, women, boys, and girls. And you get like 708. and die, include all of them, you got like 1,517. Just add up, okay. And total passenger here from Titanic is 2,225. So here the first part, right? Find property of a selected individual who will man survive. So man survive, it is this cat, this corner, right? 304 here, right? So here, this property is just 304 divided by total. So here total help us, right, to find it very quickly, which is a sample size, right? Sample space size, which is 0.150. You can keep 3, which is 0.15, right? Probability of random selected individual who is a woman and die. So woman or die, so which you can get either this woman here or die here, right? Or die. So this will be this cross, right? So one strategy we can use is the addition rule, right? Which is probably woman 422 by 2225 plus probability of die 157 by 2225 and subtract for the woman and die, right? Which is 104. So you do that formula, you get this here, right? And it will give us 0.2858. You keep 3 with 28. 8, 2, I'm sorry, 826, right? 826 instead of 8258. And then a random selected individual who is a boy given he died, right? So if he know it die, he died. Well, probably he a boy. So die given a boy. So basically now your sample space is restricted to the die space, okay? Which is now you got only like 1517 instead of the whole, right? And what probably here boy. So boy here we got 35. Right, 35. Let's see here, right? So it will be 35 divided by 1517, and you can also get 0.0231. And here like the last one, probably at least one man in a two selected individual. So you select two people, you want to find probably at least one man, right? One man. So at least one man is at least one event, which is not a man, right? Not a man. So one subtract not a man, which in this case you can see here we have 1694 men, right? So basically, if you do not men, you can add up this, right? And it gives you, let's see, 422, 60, which is 1 over, so 531, right? 531. 531. So which means like 531, which is the first is not men, right? Divided by the chunk, the whole sample space, time 530, right? Because the first one is man, so the second one is not man, I'm sorry. The second one, not man, will be 530, right? The man in. But again, here, because you can, also consider because you just sample two people from 2,225 people, which is much less than 5%, right? So you can just basically just use 1 subtract to 531 by 2225 and square power to the 2. Okay, the first one not man, second one not man. It still should give you relatively accurate compared to this result. So either way, you can look at in a way where you actually sampling these two men out without replacement, right? Or because the sample size now only 2 out of 2,225, so you can also treat them as independent. So at that time it would be 1 subtract to 531 divided by 2 square, okay, square. But here the accurate way of calculating, okay? But you can do an approximation as well. So another example about single house bedroom, okay? So here we look at we related to, try to relate two categories, number bedroom and location, okay? So number bedroom of single house at Chattanooga, Nashville, Northville, and follow. A random to one family find probability that a family in Nashville has 4 bedrooms. Probability that a family either in Knoxville or have 2 bedrooms, and probably family have more than 3 bedrooms, even in Chattanooga. So for sure, it will be easier if you try to do the summation, say the location, right? You got like for this, or how many houses in Chattanooga, how many in Nashville, how many in Knoxville, and how many household like has 2 bedroom, 3 bedroom, and 4 bedroom, right? You can do the sum here. But if you kind of get used to with that, you can do also very straightforward with the calculation by just look at this simplified table, right? So the first question asking about a family in Nashville and has 4 bedroom, right? So Nashville and has 4 bedroom, which is this chunk, right? This chunk, 60. So we have 60 of them. And the sample space, which is total of household here. So you just use 75 plus 130, 120, 121, 5, 160, and so on. So the total household here, you got 8640 if you do calculation. So you use 60 divided by the sample space size, right? Sample space size, which is 840, you get this property. So this is a property of a family in Nashville and has 4 bedroom, okay? About 0.0751. And what property up in Knoxville all have 2 bedroom, the all event, right? Either Knoxville or have 2 bedroom. So Knoxville, which in this case you got, you can use the addition rule, right? Probably Knoxville, probably 2 bedroom, and probably Knoxville 2 bedroom. So Knoxville, we get how many family here? 11760. So this is probably Knoxville divided by the sample space size. The probability of 2 bedroom, which is in this case, right? 75 plus 125 plus 100, and divided by sample space. And both Knoxville and 2 bedroom, which is 100, the corner here, right? So you drag here. So if you do calculation, this is the number you get. What the probability of the family have 3 bedroom or more given the in Chattanooga, okay? So this is the conditional probability, right? Conditional probability. So will be equal to A and B divided by BB, right? So greater equal than 3 bedroom, and in Chattanooga divided by Chattanooga. So the denominator, which is Chattanooga here, which is you got 75 plus 130 plus 120 divided by sample size, and the numerator, which is 3 bedroom or more, right? Which is 130 plus 120 here, right? 130, 120, okay, and divide by 840. But for sure, if you kind of efficient enough, right, you know how this rule work, and you can see just now, instead of look at the whole sample space, right, you should look at the Chattanooga, right, row here. So in Chattanooga, you got like 75, 130, 120, and you just look at the 3 bedroom or more in Chattanooga, so 130 plus 120. So 130 plus 120 divided by the summation of this row, it also gives you exactly here. And here you can see that when we go this track, the A40, they will cancel out, right? So which means it just left us the track we just say, right? So we only look at Chattanooga row, and we look at 3 and 4 bedroom. So let us look at the quiz 331, where we have a contingency table related the flavor of the soft drink and the age, okay? So we have 3 flavor, cola, root beer, lemon. In age, we divide people by group less than 21, 21 to 40, and older than 40, okay? And the data is given at the table. So we want to find the property if we choose a person at random, right? And that person will prefer cola or older than 40. And then prefer lemon n, okay? So we're gonna n even 21 and above, right? And then if we choose 2 people, right, randomly without replacement, okay? So if we take one person out from the data, we don't put them back, right? And we find out that one like cola and one like root beer. And so typically like this can be treated that the dependent, right? Dependent. But given the data that big, actually it won't hurt much if we treat them as independent, right? But we go into detail about that when we solve the problem together, right? So say the last one, right? Two random chosen people with replacement, one like cola and one like root beer. So in this case, we get a independent, right? Because we choose replacement, which if we choose the first one and then we put he or she back, right? And then we draw another draw, right? So two event, the first event has nothing to do with the second event. So let us work on this problem together, okay? Let me insert a slide here. Here table we got. Use it here, okay? Let's make it a little bit smaller here. Okay, so we have space for doing the problem, right? Here we got here, okay. So see what the A here. Prefer color or older than 40, right? So the all event. So basically here probably A, E, color, okay. Or, okay, which is a cup, okay, the unit. Or greater than 40. So if we look at our table, prefer color or older than 40, this is all event, right? Or, okay. So which is probably color. Addition rule, right? Plus property of older than, okay. 40, okay. And subtract color and 40, right? Okay. We can denote it in a more official way, but I want to to say some of the writing. Okay, so I just put it this way, but you understand, right? A the event they prefer cola, B the event they older than 40, right? You can put that way, and then you can write that. But anyway, this works too. So cola, which is you get 80 plus 110, which is the first column, right? 110 plus 100. What the sample size here? Sample space size, you got like, if this you do the calculation, you got 290, right? 190, 290, right? So here you get 230, 332, right? Is that correct? Right. There would be a people. 230, 330, 332. Yeah. 130 and 61, which is 191, right? 191. The same thing you can do for the less than 21 group, which is you got 200. If you do the sum here, okay, so to do the sum first, and 280 here. If you do the 21 to 40 group, you got 170, 270, 270. And older than 40 group, you got 202, 263, right? 263. Okay. But more or less now, let's look at the summation here. You got the total, the grand total will be in this from this data, right? 280 and 270, you got 550, 550 and plus 200, 750, A13, right? A13. Correct? A13. You can check, okay? You can check. So total number of people will be A13. So will be divided by A13. And older than 40, here you just calculate, right? Which is 265. 263, I'm sorry, 813. And subtract the common, right? Colder and older than 40, you got like 100, right? So just perform this calculation, right? Calculation. And you get your number, okay? In your job. Prefer lemon and from 21 and above, right? Lemon here. N, okay, N. So the N event 21 above. So if you look at here, right? 21 above, which means either belong to 21 to 40 or 40 and above, right? So this is the category we care about, right? So which in this case be 60 plus 61, lemon N, right? So divided by 8, 13, right? So you do the calculation, this gives you this probability. Two random chosen people with our replacement, one like cola and one like root beer, right? So basically here like the first like cola. And the second root beer, right? Can be the first like root beer. The second like cola, right? So if we finish, we can calculate one, we can calculate the other thing in a similar way, right? So because here you choose people with our replacement, right? So they depend on event, okay? So let me just focus on one case first, okay? And other will be similar. So will be probably the first like cola times the second like root beer. Even the first like cola, right? This is like the multiplication rule, right? Given that for like cola. So the first person who like cola, remember here we choose with our replacement, okay? So we don't put them back. Is that the property would be A13. And like cola, we have 290 people, right? Now, because you know that the first person like cola and you didn't replace that person back in the sample space, right? So now your sample space is shrink down a little bit, yet 12. And number of people, the second like root beer, right? The root beer group you still have 332, right? 332. So this is give us the first probability here, right? But we do have another guy, right? Which is the first like root beer, the second like cola, right? So this case will be the first like root beer. The second guy will be the first root beer times second like cola given the first root beer, right? The first root beer. So basically this second guy, which you add up, you need to add up a second guy, which is the first like root beer. Root beer you have like 332 times divided by A13. And because you didn't replace it, put him back, right? So you get a new sample space given the first like root beer and you didn't put them back, right? And you had 8, 12, and now it's probably like cola, right? Right. So pretty much you see that, you switch things around a little bit, but it got double, right? Double this 890 divided by 813 times 332 divided by 812, and another one which is 332 divided by 813 times 290 divided by 812. So the two, basically they just the same, right? The same result. So basically just double. You can perform a calculation, okay, and see it. And the last question is, you random chose two people, right? With replacement, so which means you put them back, right? So in this case, the event we treat as independent. So just do the same thing, right? One like caller and one root beer. So the first like caller, second like root beer. I drop it right here, okay? Like here. Plus first root beer, second caller, right? Again, the same thing, right? First caller, times second root beer, given first caller, right? Plus first root beer, second caller, first root beer, okay? So this guy is just corresponding to the first probability here, and this guy just corresponding to the second here, okay? So the first caller, which is, we have a caller group, which is 290, right? 290 divided by 813 time, here, remember, you put them back, right? So you still have 813, okay? So the probability you get the second root beer is 332 divided by 813, okay? Because you put back, right? So different with previously, you have 332 divided by 812, but now you still get the same thing, okay? And plus with the same thing, right? The first like root beer, 332 divided by 813 times 29813, okay? So you can perform this calculation and you also get the result. And when you get the result, you should be able to recognize that the C and the D, okay, the result from C and D, it won't differ much. And the reason here, you see that you sampled only two people, right? From a sample space of the size of 813, okay? So 2 is much less than 5% compared to 813, okay? So this, basically you can treat, even though the C and D, they different, right? It's slightly different in the way we're sampling. But the way we can treat C, we can also treat like D, okay? So if you want a fast calculation, you don't want to look at the conditional probability. So indeed, it can be, you can treat at independent event, right? So basically, like here, I write the formula this way. But if you can treat at independent events, so you can see that this property, right, for the D, you do with replacement, right? So the second get a root beer and the first get a caller, it had nothing to do with each other, okay? Because you put the person back. So basically, this is just property of second get a root beer, like root beer, right? Okay. Equal, okay? Yeah, same thing. This guy just property equal second like caller. That's it. You can see that the sample space doesn't change, right? Doesn't change. So this quiz also in our chapter 3 here. Thank you so much for your attention. And I'll see you in chapter 4 about discrete distributions.